This is regular physics, linear momentum problems, page 219, number 33. This problem is very similar to the previous problem with dropping the hay bale. There's just as much kinematics involved as there is linear momentum. So we see this dancer up at her apex of 0.32 meters. And she is going to accelerate at 9.81 until she strikes the ground. So I need to know her impact velocity. So what we do is we go to our kinematics, and there's probably a dozen different ways to do the kinematics. But probably the quickest way to do the kinematics is what we call our equation number 5 here. Everything is happening in the vertical direction, so I know my distance in the y and all my other values. Let's plug and chug into that, and I can calculate her v final. Now it is negative, right? That just means that as she strikes the ground, she's going downward. So we can put a down arrow. Or in this problem, I've just kind of carried through with the negative. Okay, so let's continue on. Now I know that her velocity at what she hits, the momentum is very easy. She has her mass times this strike velocity, and that gives me this momentum. Now also a vector quantity. This momentum as she hits the ground is a vector quantity going down, simply multiplying v final by her mass. Okay, now what happens after she strikes the floor? After she lands on the floor, her velocity is 0. Therefore, her momentum is 0. Okay, kind of a redundant question then what's her change in her momentum? Well, simply she lost everything she had. So since her final momentum is 0, and the momentum she had previously was her mass times her impact velocity, well, she just loses that quantity, and that's her change in momentum. So actually the number ends up being the same, right? Ends up just being this P, or this momentum, as she strikes the floor. Okay, and we know by impulse momentum theorem that my impulse is equal to my change in momentum that I previously calculated. All right, so if I have that number, then I know it's my change in momentum. Then I know it's also my impulse. Now, I can also define impulse by average force times delta t. We know this change in momentum quantity that satisfies the right-hand side of the equation. Delta t is given in the problem, so I can back calculate this average force required for her to lose all of this momentum. Okay, now the last part, we've calculated this force, and it says compare this stopping force with her weight. And this is just a matter of perspective question. Her weight is very easy to calculate, just m times g. And we see she weighs about 589 newtons. And it says, okay, compare that to this stopping force. Is it bigger? And if it is bigger, how much? Usually by how much, we mean how many times bigger. So we usually want a ratio. Is this average force twice as much, 3 times as much, 3.89 times as much? Just divide the force average by her weight. That will tell you how many times bigger it is than her weight. And that's what they're looking for.